Okay, this is exam 3, fall 2022, exam question number 1. This is a mouthful one, so I'm just going to read through the question and then we can jump right in. So 1A is draw the major products for the following elimination reaction. Is this an E1 and E2 reaction? And then predict how each of the following modifications to the reaction conditions will affect the rate of the reaction in the problem, faster, slower, or same. Provide an arrow pushing mechanism for the elimination reaction in part A, and what changes to reaction conditions will lead to the formation of the other constitutional isomer without changing the bromoalkene. So let's just start with taking note of what we are actually doing the reaction with. So KO2BU, that's just a fancy way of saying this. So it's a pretty big molecule. We could put that this is a big base. So that is our big bulky base. I know that's how people like to say it. So this is going to be our big bulky base. So something that we know with bulky bases is that they are usually going to be an E2 reaction. You can't do an E1 reaction with bulky bases. So we know this is going to be an E2 reaction. But where exactly is this going to happen? Is it going to happen here? Is it going to happen here? We don't really know right now. So something else that we can also point out is that this is that where our bromine is, that is in a secondary position. So since it's in a secondary position, we're able to know that it's going to have to take where this is able to take it from. So this is really big and bulky. So you can't just take the hydrogen. So there's a hydrogen here and there's a hydrogen here. Since it's such a big and bulky base, it's more likely to take this hydrogen. So it's going to take this hydrogen, and then this is going to leave, and that's going to form our double bond, which I can draw right here. And then that is our answer. So we answered that part. Let's just move on to question B then. So predict how each of the following modifications to the reaction conditions will affect the rate of the reaction in the problem 1A. Faster, slower, or same. So let's think about this. Our base is going to be attacking this hydrogen, removing it, and then it's going to be going here, and then that's leaving. So if we were to decrease the rate that our base is attacking, that is going to make the reaction slower. And then if we increase the concentration of the bromoalkene, so that means that there's more of these for our base to attack. So that is going to make it a faster reaction. And then if we were to change the bromine to iodide, so what we know about our leaving groups is that iodide is a big group. So that means that it's more likely to leave. So that means that it is going to be faster because of this. Perfect. So now we move on to C. Let's actually provide an arrow pushing mechanism for how we got our product in part A. So let me just redraw what we have here. And then I'm just going to draw our hydrogen right here. So there's 3 hydrogens. You don't necessarily have to draw out every single hydrogen, but you want to draw out the hydrogens that are going to be taking place in the reaction. So with that, we are going to have our base come. Oh, we had to also draw our base. My bad. I'm moving a little bit fast here. So we're going to have our base come in, and it's going to grab onto this hydrogen. And because that hydrogen is being grabbed, the electrons from that bond is going to go right back to that double bond, or go and form a double bond, and that is going to cause our bromine to leave. So then we're going to get our product right here. And then notice with that this is not being touched. It's nothing to do with the reaction, so the stereochemistry is going to stay the same. Oops, I had been drawing it without an extra carbon. That's my bad, everyone. So that is our answer for part C. And then for D, 2 constitutional isomers are possible. Elimination products from the bromoalkene. What changes to reaction conditions will lead to the formation of the other constitutional isomer without changing the bromoalkene? So we aren't changing anything about our original starting product. So what we can really do is change what our base is. So I had mentioned that this was a big, bulky base. So some way that we could change this is by using a less bulky base. So using an example of that could be H2O. H2O. You can do MEOH. You can do an aprotic solvent, so you could have just done like I minus. So like that's just an example. So that would change like our reaction conditions completely. You don't necessarily need to write these. I was just giving you guys a better idea, but the answer to this is using a less bulky base, because this would cause our reaction to be a little bit different. Like we could possibly have been able to take this hydrogen or this hydrogen. Really just depends. So yeah. Okay. Number 2, provide the reagents that will produce the following aldehyde and ketone from ethanol benzene. Draw the structures of the enols. These carbonyls are in equilibria. Okay, so first thing, what exactly is an enol? I'm going to write what an enol is up here. So we have OH, and then we're going to have a double bond somewhere. So we have our O's here. Ooh, that's not really the one I wanted, but there we go. We have our O's here. And we want to somehow turn those into enols because we have the carbonyls. So this is like after the reaction's done. So after whatever we use at our reagents, this is already done. But the difference is that one of them is an enol and then one of them is a carbonyl. So we have the carbonyls and we just need the enols now. So they aren't necessarily asking us to draw the reactions, but I'll just go through it really quickly. So whatever reagents is, it's going to be an acid and a base. So let's just picture that we have our acid here, and then we have a base that's like in the end. So our oxygen is going to grab onto the hydrogen, and then that is going to cause it to be like, I'm not going to draw the whole thing, but like picture will be OH plus. And then in order to make that stable, the base will come and grab the hydrogen, and then it'll push those electrons back onto the oxygen, or no, sorry, that'll push the electrons of the hydrogen onto the carbon, the hydrogen back onto the carbon, so then that gives us our double bond there, and then that will break that double bond and push those electrons up here. But not necessarily what you guys needed. I just did that just to be extra, but essentially we're turning our carbonyls into enols. So we basically go through that process for the bottom one as well, but it's essentially the same thing. So we know that it's going to be, our product is going to be, I just want to make sure I'm not adding anything extra. And then those are our carbonyls. So the key thing to notice is that there's no change in this one or this one other than the fact where the double bond's going to be. So it's just switching it from an enol to a carbonyl. And then that's that whole process where we go through and we're making all the changes. And then same with this one down here. But notice that we grabbed the hydrogen from over here and not here. So the double bond wouldn't be here because there is no hydrogen to grab from here. So let's think about the placement of where our hydroxyl group is. So we have one that's like not really ideal, like this is really not ideal, and we have one that's very ideal. So we know that the one that's not ideal is anti-Markovnikov, and then the one that is ideal is Markovnikov. So we learned a few different reactions that got us the solution from a triple bond that we have here. So with triple bonds, we only have a few reactants. It's not as much that we have with the double bond. So with the triple bond, the first thing that should come into your mind for the anti is our CaBH2 or Ca2BH1. It's kind of strange, but it's the first one that comes to mind for me. So Ca2BH, and then the second part of that is going to be NaOH, H2O2, and then remember that's our anti-Markovnikov, so that's what we wanted for that. And then we have our Markovnikov, it's going to be H2O, H2SO4, and then HgSO4. And that's going to be our Markovnikov product. So that's the answer for number 2. Number 3, it says, give the products with stereochemistry indicated of the following reaction. Will it undergo SN1, E1, SN2, or E2 reaction? Give a brief explanation of your choice. So the number one thing that I usually do when it comes to these problems is 1, identify your nucleophile. I'm going to say nuke. And then 2, identify electrophile, elec. So nucleophile attacks the electrophile. So in order to do that, we should look at what our nucleophile is. So our nucleophile is going to be this. And what you're going to notice about this is that this is a, I'm blanking right now, a protic solvent. So it's just a fancy way of saying this. And honestly, for me, it kind of looks like water. So like protic solvents are going to be like the water, or it's going to be the stuff where it's not necessarily like a strong base. So protic solvents aren't strong bases, but they are a base. So like water's a base, but it doesn't necessarily have a negative charge, but it's still our base in the situation. So we know we have a protic solvent, and then we also know that we have a tertiary leaving group. So we have 1, 2, 3 groups attached to our leaving group. So that means that it's going to be a tertiary. So when it comes to, let me just put that there. So we have a tertiary group, and then we have a protic solvent. And when you think about like all your reactions, that should sort of go off in your head whenever you see tertiary, that it's going to be SN1, E1, or E2. SN2 cannot happen with a tertiary one. So if we go by that, we also know that we have a protic solvent. So that means that it's going to have to be SN1E1 is going to be our answer. So SN1E1 is going to be the type of reaction that we go through. So now let's go through and give what our solutions are going to be. So for the E1 product, you notice that with our given structure here, that both of these sides are identical, other than the Cl and this part being here. So it doesn't really matter which hydrogen we end up taking from, but we're going to end up taking from one of these hydrogens here. So I'm just going to take from the left hydrogen, here. So that is going to give us that. And there's no more stereochemistry on this carbon that we have here because it is an identical molecule, or they all have, there's no symmetry. Or there is symmetry, my bad. So then for the S1 product, we're going to have S1, remember, this is just where our nucleophile attacks the electrophile. So we have this attacking the bottom, our leaving group leaves, and then that is what we have here. And then when our leaving group leaves, we're going to have like technically a plus here, and then our base just comes back in and it grabs that for us. So then this is going to be our products. And then we can go back to, again, like our reasoning in the beginning. So we had a protic not strong, or I guess poor nucleophile slash base. And then we had a tertiary electrophile. And that is our answer for number 3. Okay, for each of the following reactions, draw the structure of the major products. Indicate stereochemistry where appropriate. Okay, so this one's kind of a mouthful, but it's not actually too bad once you think it through and if you remember all your properties. So first thing, they throw us a curveball, kind of, because they want you to draw out what the original structure is. Well, not necessarily, but you're going to need to know the original structure before you attack this problem. So again, I'm pretty bad when it comes to drawing out hexene versus pentane, things like that. So I like to count out my carbons. So I have 1, 2, 3, 4, 5, 6. And trust me, I'm doing this 100% for me, not really for you guys, because if I don't count it out, I will get it wrong. So 1 hexene, so that means that our alkyne is going to be on the first, or between the first and second carbon. So it's going to be right here. Awesome. Cool. So that is our structure then. So when I originally started recording this problem, I tried to just draw it out straight, but or just to like give you guys the answers technically, but I think it's a little bit helpful. I like drawing out the process at least. So we know we have 2 equivalents of HBr. I'm going to start on the right. So we know that it's just 2 equivalents of HBr. There's no sort of peroxide or light or anything like that, so we can sort of just go by what we know. So the reaction for this is going to look something like this. I'll do it really quick for everyone. It's going to look like this. It's going to attack the hydrogen. The bromine's going to go there. And then there's going to be a plus on there. It's going to be double bond. And the BR is going to attack there. And then we're going to have this. We're going to have another bromine. And then we're going to go through it again. And same process all over again. And then our final product is going to look like this. 1, 2, 3, 4, 5, 6. So then that is going to be our final answer here. And then for 1 hexene, and then we're going to have 1 equivalent of Br2. 1, 2, 3, 4, 5, 6. You guys can hear me counting like it's just something I do. So comes the Br2. Our triple bond is going to attack the Br, and at the same time, it's going to give these electrons to there. It's going to basically attack right back to. It's going to basically attack right back to the double bond, and then oops, let me not. So then the electrons from bromine is going to attack right back to that corner, and then that's going to go away. And then we're going to have our little, I like to think of it as like a little pyramid at least. So we're going to have that with our BRs here, and then that second BR minus that we got from over there. It turns into that at least. So then we have our final answer is going to. So I'm going to have to erase it. But basically, it's like you get this little, the pyramid. It's from exam 1 and exam 2. But essentially, you're doing that with an alkyne. So you're going to get our like essentially the same thing that you get with a double bond, but instead now you're going from a double bond to a single bond to a triple bond to a double bond. So the product is going to look like this. We have a double bond, and we're gonna have a bromine up here, we have a bromine down here. And then that is our answer. 1, 2, 3, 4, 5, 6. Awesome. So, yep, those are our answers for right here. Obviously, they didn't need you to draw out the reactions, but I just did that so that you'd be able to be like, why'd you put that there? So for the next one, so here's our keywords again. So what I was talking about the first one and why it wasn't so difficult is because this is stuff that we've done before, but we were just doing it with the triple bond. But now we're doing it with a double bond, and for one of them we have peroxide and light. So I'm actually going to highlight that because very, very important for you guys to know. So peroxides and light, think immediately anti-Markovnikov. And then for anything other than that, just think Markovnikov like normal. So for this one, we have I'm going to start with the right. It's something that you know how to do, something you've done before, shouldn't be alarming. So we have that, and we have our HBr. Our double bond is going to attack the hydrogen. It's going to have our electrons go to the Br, and then from there, you're going to have this, and then remember, our charge is on the most stable part of the electron. We cannot have our electron be here. That is a no-no. Do not do that. So we have our electron at that positive right there, and then we have our Br negative, and that is going to attack there, and then we are going to get the product of there. Perfect. And there's no structure because there is no chirality. It's achiral. Sorry guys, I'm getting over sickness. So then from there, we now have our anti-Markovnikov, which is a little bit more complicated when it comes to mechanic-wise, but I could draw it out really quick. So we have that, and then we have our HBr. Our bromine, or our double bond, is going to go to our bromine, or not double bond, but like think of it as like the initiation propagation type thing that you guys have learned before. So then from there, you're going to have this. Our bromine is going to go to the anti-Markovnikov, and then we're going to have our blanking. We're going to have our man, guys, I am blanking so hard right now. Our radical. There we go. Sorry, blanking. So our radical, remember we want our radical on the most stable. So the reason why we put our radical here is the same reason why we put our cation here. So our radical needs to be in the most stable spot, so that is why our bromine is right there. So our bromine is right there, and then after that, so we have this, and then we have our bromine here. So then after that, our hydrogen, it's going to go to HBr. We need to satisfy this radical here, so our radical is going to grab this hydrogen, and then those electrons are going to go to our bromine. So yeah, or that one electron. Sorry, it's a fishhook. So basically, our answer is going to be, and then our bromine here. And then notice with when we added our hydrogen, we don't have a chiral center anymore. So when we added that hydrogen here, it could have pushed this carbon up front, or it could have pushed it back. So our answer technically is going to be, could have pushed it forward, or it could have pushed it backwards. And then those are our answers right there. Awesome. So then last one, we have our 1 bromo propane and 2 bromo propane. So this is the opposite of the first one, where they gave us the initial So now they're giving us the reactants in us, so we have to write that out. So we have 1 bromopropane, 1, 2, 3, and then 2 bromopropane. So 1, 2, 3, and then we have our Br right there. So when you look at this, we basically have the same thing, but our bromine is placed in 2 different spots. So for the reaction on the right, we are going to have an E2 reaction, and the reaction on the left, we're going to have an SN2 reaction. And then again, this is all because of where our bromine is placed. So because our bromine is placed in the center, it's really hard for this big base to get inside. So that is why we have an E2 reaction. With this bromo on the outside, it's really easy for it to reach the center. Like, it's not too condensed. Like, it's like a pack of hot dogs. Like, it's easy to just have this go inside. Whereas for this one, it would have to be going inside and so on and so forth. So since this is an E2 reaction, pretty simple. I'm actually just going to draw it with the highlight and just have it go away. So we have our hydrogen here, going to attack that hydrogen, that's going to go here and force our bromine away. And that is going to give us, really simple, it's going to have it like that. And then that's our answer for this one. And then for our one on the right, we are going to have an SN2 reaction. So the electrons are going to, leaving group's going to leave, and then yes, leaving group's going to leave, and then that's going to cause us to have a, okay, so, let me count it out. Oops. So here we have 1, 2, 3 carbons, and then we have our bromopropane. So technically, we're going to have 6 carbons on this connection now. So we have 1, 2, 3, 4, 5, 6. 5, 6. And then we are going to have our triple bond on the second one. So it's going to come in and attack yeah, so it's just going to come in and attack at this bottom one. So basically, it's just going to come in and attack right here, essentially, making this leaving group leave. So picture, it's a little hard to visualize this one, because if we have our 3 coming in, then technically our carbon is going to be 1, 2, 3. And if we're having an attack here, then that's when this one's going to start. So our triple bond is going to be on here, because we have our 1, 2, 3, 1, 2, 3, and then this is where it connects. 1, 2, 3, 4, 5, 6. And then that is going to be our answer. A little bit hard. Just wanted to make sure that I wasn't leading us astray. Because again, with these, you really have to make sure that you count in, that you keep all of your carbons, especially with these SN2 reactions and E2 reactions. So awesome, yeah. Okay, so number 5. Show how to convert the geminal dibromide shown below and the product shown below in high yield. Please also draw the products of each step. Please note that more than one answer is possible. We suggest 2 steps. However, other correct answers are possible. Okay, so since we're going to go with the 2-step method, usually it's best when it comes to these exams just to stick with the 2-step method, because the more you put down, the more likely you are to make mistakes, and you don't necessarily want that. So if you at least try with the 2 steps, let's just jump into it. You'll see what I mean. So let's start with our original product. We have this this is our structure right here. And we're going to want to note that it is 2 steps. So we see that we're starting with not single bonds, an alkane with 2 bromines, bromides, bromines. Yeah, bromines. We're starting with 2 bromines. And then we're reducing that down to have no bromines, and we're also going to have a double bond. So the first thing that I'm thinking about is getting rid of those bromines. And the way that we can do that in one step is to have a really strong base. So there's a difference between a strong base and like a really strong base. So whenever you think of wanting to rip off both bromines, think of having a very strong base. So there's like a strong base, which is just like, let me think, um, like a NH2, that's considered a strong base, or like a OH minus, that's considered a strong base. But then there's things like LDA or NaH. Those are just really strong bases that we know about. So um, those are that is gonna reduce it down to that triple bond, because there's really no way for us to go from a just without being more than 2 steps. So this is going to be the first part. So I'm just going to write really strong base. So this really strong base, it's going to reduce both of these bromines, giving us this triple bond, which is what exactly we want. So if I were to do something like OH minus, that could possibly just lead to a double bond. And then from there, if you have an OH minus, you wouldn't necessarily get this Br2. So you'd only be able to do it once in order to reduce it. So what they're looking for here is just a really, really strong base in order to get that triple bond. Because realize with that triple bond, that is what we want for this step. So then after that, we have our really strong base. And then we notice here how we're going from a triple bond to a double bond. Really simple. And also notice I have kept our carbons here. 1, 2, 3, 4. So these are our 4 here. And then this really strong base grabs these Br2s, so on and so forth. So then from there, we're going to want to use our knowledge of things that reduce our triple bond down to a double bond. And that's the first thing that I think of is Na and NH3 as a liquid. This is just one of those general knowledge things that I highly recommend just knowing. With the alkyne, well, for the alkyne types of reactions, you don't necessarily need to know the actual reaction steps. So it's just something I recommend you knowing going into this exam, is just knowing what reduces a triple bond down to a double bond, and that is going to always be NaNH3 with a liquid. So yep, that is number 5. So number 6, for the following allylic bromination reaction, draw the structures of the radical intermediates and products formed during the steps shown below. Draw the resonance structure of radical intermediate 2. Remember to draw all possible stereoisomers of the products. Draw curved arrows to indicate the movement of electrons. Indicate the major products. So this is one of those ones where you just got to work from the bottom down. So the first thing that you're going to want to remember is all of the curved arrows. Make sure that we're drawing those correctly, as well as the radical intermediates and products. So these are definitely things that you want to know. So, yep, let's just start. So the first thing, this is something that most people might forget about, is that there is one step right here where you're going to need to draw the arrows out. And remember, with radicals, think of the fish hooks. So I'm going to have a fish hook going out there, a fish hook going out there. Notice how I'm drawing the little fish hooks and not a full arrow, because this is indicating one electron going to these bromines. So that gives us this. So we're all set there. We did that first part. So now the second part is they want us to do the propagation of this equation, but notice that they didn't really give us the product, so we had to draw out the product ourselves. So R3-methyl-1-cyclohexene. So the things I notice is we got hex, so we have a 6-ring cyclohex, so that means that we're going to have a 6-layer ring, which I have drawn. Awesome. And then we have 1-cyclohexene, so that means that our double bond is going to be on number 1. So if we were to name these out, we can sort of do however we want. But I'm going to name my 1 being here, 2, 3, 4, 5, 6. So with that being said, I'm going to put the double bond being right there. And then if this is 1, 2, 3, we have our methyl being on 3. So we're going to do that here. But notice it says R. So remember, we're going to want to use our center, our chiral center, to figure out which one is R and which one is S. So if we have it being, if these are our 3 factors here, we have this being the first molecular heavy one, this being the second, and this being the third. So with that, that is going to be our rotation is going to be to the right. So that's exactly what we want. So let's push that carbon forward. So then it's going to be 1, 2, 3, and it's going count clockwise. So that is going to be our structure for our R3-methyl-1-cyclohexane. So then from there, we have our hydrogen being in the back. And then from there, we are going to have our bromine and our hydrogen doing like the propagation step. So from there, our hydrogen, or this bond that is right here, is going to reach out and meet halfway with the bromine. And then that is going to form. And then this little electron that is going to be left in this bond is going to go back to this chiral center. Let me make sure I draw this so you're able to see. So that's going to be going to that little chiral center. It's a little bit hard to see, I apologize, but it's going right here. So that is going to give us the radical intermediate 2, which is going to be, let's just draw it out as it is. We have our this here, and then we have this. Notice how we don't have any stereochemistry anymore because this hydrogen is gone. So now we just have this radical right here. So this is our radical intermediate right now. So then in order to terminate this this step, remember we're just trying to get rid of this radical. What is this radical going to interact with? So let's just draw what our radical intermediate is and put it right down here. And then we have this, we have that, and then we have this. And we have our radical. So then from there, our radical is going to reach out and our bromine is going to reach out. And then that is going to form a bond. But remember, this bond can be either front or back. So this is going to give us our product 1, which is going to be, it's going to either have the bromine being front or our bromine being, let me just be consistent with which one is going to be here. Bromine being in the back. And our, bromine in the back or bromine in the front. And remember that this is a 50-50 mix. So that is going to be our product 1. But then remember, or something to notice here, is that our alkene, or like the alkene or the double bond, it's here. And remember, it's going to be most stable when it is closer to that, closer to the cyclohexane, because we don't want it to have a degree of 2 or 3, where we'd prefer a more stable. So the closer it is to other ones, the more stable it's going to be. So then from there, they want us to show resonance. So remember that with these cyclohexenes, or like the cyclos, we're able, or the benzenes, my bad guys, I'm like slipping on words. The benzene is that we can have this move either here or here. Obviously this one's the most stable one. So let's work on doing that in this radical intermediate 2 here. So we're going to start back with our radical intermediate 2 like we have above, but this time we're going to have the this electron go to form a double bond with the electron from here. And then from there, we're going to have our electron from that double bond go to this carbon instead. So then from there, that is going to give us the radical intermediate 3, which is going to look like this. So then notice how this is in a third degree bond. So this is stronger than this per se, because we have our radical being up in the top, but then our double bond, it's not really as stable. So then from there, just going to move down a little bit. So then from there, we're going to take this radical intermediate 3 that we had just drawn up here, and we are going to have it do the same exact thing that we did with radical intermediate 2. We're going to have the electrons meet in the center and draw a bond. And then this is going to be our final product here. We're going to have our bromine. Our bromine can be up front, or our bromine can be pushed back. And then the major product of this reaction is going to be product number 1 or 2. So obviously, we're going to want to look at our product 1 and our product 2. Oh, and then remember, 50-50 mix. So we're going to want to look at this one and this one. So, oops, I forgot a bond right there. So then when it comes to the major product of the reaction, it is actually going to be product 2, because of our double bond that is here. Our double bond is more stable here, since it is closer to a tertiary connection. So that is going to be our product 2, and it's more stable this way because it allows the product to spread out more, and it also allows it's a more stable resonance structure. So overall, in general, this was a way more stable resonance structure than this one, which is why our product 2 is going to be the major product of this reaction.